the program lied to us. This is not AkandW.Islam. This is Thomas
Bertalan.
From University of Atlanta. He's going to tell us about the work on OpenMG, which is a new multi-grid implementation in Python.
All right, so I'm Tom Bertalan, like I said. I just recently graduated from UA, and this is a pure Python implementation of multigrid solver. So it's not as fast as possibly PyMG other multigrid solvers, but it's designed to be easier to read so people can get started in understanding multigrid algorithms. So I'm going to talk about some motivation for multigrid, give a little bit of background for the math for it, and then distinction between algebraic and geometric multigrid, and then a little discussion on our implementation. So we have 3 examples here of some problem domains that would definitely benefit from multigrid solvers. The first is our field, which is pressure-driven flow of oil and gas through underground reservoirs. Perhaps in mechanical engineering, you have a heat transfer problem where you have this heat equation describes distribution of temperatures across an object. So actually similar to our porous media problem is diffusion of solutes through something like a brain. So you can have like MRI data for diffusion across the brain. You can use that to reconstruct the neural tracts. So in each of these examples, you have some kind of a constitutive equation that describes the relation between some property across the boundary to itself through a differential equation. Looking at this one example of temperature across an object. For example, imagine we have this 2-dimensional object, which is hot, square. We drop into some cold liquid, so we have a boundary condition of a cold temperature and then a hot object. And we expect to have this kind of a temperature distribution across the object, but that has to be solved for. So this being a computer, we have to discretize the problem into a certain number of points as opposed to a smooth solution, which you'd have if you had an analytical solution. And we number those interior points separately from the boundary. And the reason we do that is because being that it's immersed in this cold fluid, we know that the boundary points are a particular value. So for example, if it's ice water, it would be 0 degrees C. So we can replace the interior numbering scheme of 2 indices with just single index per number, which allows you to have a formulation where the interior is just a vector of points. So again, the constitutive equation for this example problem uses this Laplacian operator. And this right-hand side with the time derivative can be eliminated if inside the object there's no sinks or sources. There's no sources of heat that are generating temperature increase, or there's no places where heat's being drained away. This is not necessarily true in our porous media problem, where you might have a well injecting CO2 and another well pulling out oil. But if you do set that to 0, then you have this simpler equation, the Laplace equation. So this is a very simple equation. It's good for a model problem to solve. So this Laplacian operator is in fact the sum of the unmixed second partial derivatives. And of course, this being a numerical algorithm has to be changed from a continuous operator to a discrete operator. So that's where you get the coefficient matrix A in this AU equals B equation. This A has to somehow represent, again, the sum of those second partial derivatives. So one possible formulation is to look at the difference in forward difference and reverse difference, which gives you a second partial derivative, which is a central difference. And you do that separately for the x direction and the y direction to get this 2-dimensional Laplacian coefficient matrix. And you see we have a 1, -2, 1 pattern in both of those. And when you sum these together, since the Laplacian is in fact the sum of these second partial derivatives, you get a 1, 1, -4, 1, 1 coefficient pattern for the surrounding points of bottom, left, right, and top. And so I think it's the 5th line in that coefficient matrix. You can see that same 1, 1, -4, 1, 1 coefficient pattern. And so this here is one possible example of a matrix equation that we would solve with any sort of a solver. But the information that's applied is the coefficient matrix on the left, and the right-hand side B, which includes information about the boundary conditions. And what has to be solved for is the U vector in the middle. So the classical methods of solving these are direct methods, of course, like Gaussian elimination, and iterative methods. The benefit of direct methods is that they're accurate and you know exactly how long they're going to take. And disadvantage is that they're slow, and for very big domains, that exact amount that you know is a very large number. Iterative methods can be made faster, and you can make a trade-off as you want to between accuracy and speed, but they might not necessarily converge in a reasonable amount of time, which we definitely see later on here. So a multigrid problem, the main concept between multigrid solutions is that you look at the problem at different levels of resolution. So again, we start by knowing the boundary points, and then on the interior, you do an iterative solution, but you stop at a very small number of iterations. For all of our example problems, we found that one iteration was sufficient. So it gives you a very low quality approximation to the solution that you're looking for. But then you want to correct that with some kind of a correction factor, but rather than solving for the correction factor across the whole of the domain, you only solve in a subset of the points. So in this particular coarsening pattern, the coarse points are just every other one across for each of the dimensions. So you define this coarse set in 2 dimensions has 1/4 number of points, and 3 dimensions has 1/8 the number of points. On this coarse set, you solve for a correction factor directly. So that would be more expensive if we were solving on the fine set, but on the coarse set, it's acceptable to do a direct solve. And the definition of what a coarse set is can be altered to make that ratio of 1/4, 1/8, whatever, makes it reasonable to solve directly. Once you have a direct solution for that correction, you have to interpolate it across the domain. And then, when you have a correction across the whole of the domain, you add it onto your initial iterative approximation, and you get something that's closer to the true value. So, and then when you combine that with your boundary conditions, of course, you know the solution across the whole object. So what I just described is a 2-grid pattern. You have only 2 levels of resolution that you're looking at. But that was where we used a direct solver at the second level. You can instead call your multigrid solver recursively and extend this to as many levels of resolution as works well for your particular problem. So if you do 3 levels like this, where you only do a direct solver at the 3rd level, you would then call it a 3-grid, or you can have n-grid solvers. And this is what allows us to call these actual multigrid rather than 2-grid solvers. The actual innovation multigrid comes from how we make that transfer between the levels of resolution. So in geometric multigrid, you actually regenerate the coefficient matrix at each new level of resolution by discretizing the problem again at the different levels of resolution. So this makes the algorithms a lot harder to write and makes it so you have to basically roll your own for each new problem that's being implemented. Algebraic multigrids, in contrast, only require the coefficient matrix at the full resolution, the right-hand side at the full resolution, and perhaps some choice of what coarsening method should be used. So the way we do that is by looking at this correction equation, where you have the initial approximation, you want to find that v to correct it, changing this to a residual equation, and then coarsening that residual. And then you have this AV equals R equation, which you solve not at full resolution, but at coarse resolution. So by using some sort of non-square restriction matrix, you can coarsen in the first row here that residual. So by multiplying by this non-square matrix, you get a shorter residual, which is actually the right-hand side of the coarse equation. Or by multiplying and then post-multiplying this restriction matrix by your original operator, you actually generate, without having to do any kind of rediscretization, an operator at the coarse level, which is at the smaller resolution. So you see we've gone here from well, it looks like it in the picture, but we've gone from like 2 to 1 times the size of the domain. But how you generate that R matrix can be done different ways. For our simple implementation, all we have is just the average of a cell of 4 points in 2 dimensions, or in 3 dimensions, 8 points. So here, the red points are the coarse points. This is a 3-dimensional problem, and the green points are the fine points. And the 4 or 8 blue points in the corner all get averaged down to the 1 red point in the corner. That's just the particular simple restriction matrix method that we've implemented here. But more robust and actually requiring less information from the user is the method of Rugsteuben, or how you pronounce that, coarsening. And that uses the actual coefficient matrix to estimate what are the strength of connection between fine point and coarse points. It estimates also what are the best points to best summarize the fine grid in the coarse grid. So here where we had 1/8 is the weight given to each of these blue points when it goes into the 1 red point. That 1/8 can be made a different weight depending on what are the coefficients in the coefficient matrix A that's originally supplied. So for a good algebraic multigrid with a Rugsteuben coarsening method, all that has to be supplied by the user is a coefficient matrix A, a right-hand side B, and it will supply the U vector in essentially linear time. So a question that might occur is that when you're solving for this correction factor at the coarse resolution, why is it that you can coarsen it and then still expect it to give all the fine details and variation across the whole domain? And the answer is that you don't actually need to. In the context of multigrid solvers, the iterative solver is not called a solver, except it's called a smoother instead, because iterative solvers like Gauss-Seidel, which is the iterative solver we use, they actually do a really good job of smoothing out the high frequency error in the initial GIS, but they do a really bad job at smoothing out the low frequency error, which is the big changes in the solution. So because they really quickly take out the high resolution error, it's safe to represent the problem at a lower level of resolution to get the correction vector. So here we see just a Gauss-Seidel solver working by itself on a problem. And this is the frequency domain depiction of the error after each iteration. And you see that it actually does a good job of reducing the error in the middle, which is the relatively high frequency, but compare that to the left, there's almost no change as you keep going more and more iterations of the Gauss-Seidel solver. In fact, for our model problem, to get anything like a good solution with the Gauss-Seidel solver took like, I think, 12 hours or something, compared to a direct solver taking a matter of 30 seconds. So Gauss-Seidel by itself is really bad, but it's really good at getting out the high frequency error. So here again, this is not the same metric on the bottom axis, but on the left axis is the norm of the error. So I think 10 to the minus 12 is the best error that's capable with the floating point resolution we had. But you can see the Gauss-Seidel solver does a really good job on the right, does a really good job initially of smoothing out high frequency error, and then it kind of hits a wall where it can't do much better for hours and hours. And this is compared to our multigrid solver. So it does repeated V cycles where it goes high resolution, low resolution, high resolution. And in something like 5 V cycles, it gets what looks like a very similar result to the direct solver, with basically an acceptable solution. And that's a matter of seconds compared to hours and hours for Gauss-Seidel by itself. This is because it's doing it has that frequency domain effect where the Gauss-Seidel solver only does the work that it's actually good at. So here you could imagine where that ratio of number of points in the fine set to number of points in the coarse set was different. It might actually make sense to run the Gauss-Seidel solver for more than one iteration like we did. Because if there were very, very few points in the coarse set, then you'd have to actually work out more high frequency error and actually not so high frequency error with the Gauss-Seidel solver before it was reasonable to move on to the coarse resolution and then do the correction. But here, for our particular problem that we were doing as our sample problem, it doesn't really make any sense to do any more than one Gauss-Seidel solve iteration. So what this particular graph is on the bottom axis, how many of those pre-smoothing iterations were applied with the Gauss-Seidel solver before we moved to the low resolution? How many times did it sweep across the domain, taking out high frequency error? And then on the left is how many V cycles were required for to actually get to an acceptable level of error in our solution. And the right is how long it took to get there. So yes, you can see that we're reducing the number of V cycles that are required as we're loading more and more of the work of getting our solution onto the Gauss-Seidel solver. But each one of those V cycles takes more and more time. So it doesn't necessarily make sense for our problem to do any more than one pre-smoothing sweep. But that might be different for different ratios of number of points in the define of the coarse set. So here's some actual timings. Our implementation, which is all Python, no C code or anything, is for one definition of convergence faster than the Gauss-Seidel solver and the direct solver. But in order to get the Gauss-Seidel solver to actually compare, like be on the same axes as these other graphs, we had to define convergence as actually pretty permissive. So inherently, the direct solver gets a very, very accurate solution compared to the two on the left. Now on the right here, the very, very fast solver is a good production level implementation of a multigrid algorithm, which is PyAMG. So that kind of shows what's actually possible in terms of speed up. And the precision achieved there is actually very, very good compared to the two on the left. But this does show that for some definition, multigrid is definitely, in our implementation, speeding up compared to Gauss-Seidel or direct solvers. So here is, for our particular problem domain of porous media pressure-driven flow, the outer gray surface of this 3D plot is the direct solution that we would be solving for. And then from the inside, working outwards, are the results of 1, 2, and 3 multigrid V cycles, respectively, which is depicted there as the fine, coarse, fine, fine, coarse, fine, fine, coarse, fine cycles of resolution. And so you can see that it does actually converge toward the true solution, and it does so reasonably quickly. Details about the graphing of this. This is a pressure isosurfaces graph. So you have a whole 3D domain of scalar values, and we're looking at just the values where it's 23% of the difference between minimum and maximum pressures. Again, for the fine, coarse, fine, coarse, fine, so you start with an assumption that the pressure we're solving for is 0 across the whole domain. And then by the time we get to that second fine, we have some approximation to the value. And we take that as the initial guess for the second V cycle. And that's how you do V cycling like this. So I'd like to encourage anyone to go and download our code for this and have a look at themselves. It's very simple, a couple Python files that you can look through and get an idea really quickly of how multigrid algorithms work. The address is there, and I'd be quite happy to see people giving us pull requests. So, any questions? Yes.
You guys are using first order differences there. If you use any higher order on your discretization, do you have a problem with interpolation then?
You mean for generating that the initial coefficient matrix? Mm-hmm. Well, that was just a sample problem. I think multigrid algorithms, they can take any coefficient matrix A and they can work on it, but I think convergence has really only been proven for elliptical problems, like just, I think as far as the order of discretization, I don't think that is really important. It's up to the user to generate that coefficient matrix, the initial one. And so if it's an algebraic multigrid problem, generating the coarse operator matrices will just be made from the first one that's supplied by the user. So we haven't messed with that, no, but I think that for elliptic problems, you should see just similar results. Yes?
Is this just a regular solver interface? You just provide a matrix on the right-hand side?
Yeah, that's the hope, yeah, A and B. There's a lot of other extra parameters you can set to For example, a simple one would be how many grid levels do you go? Do you go fine, coarse, fine, or do you fine, coarse, coarser, fine?
You can just drop this into a PD solver and apply it.
Basically, yes. And if you look at PyMG for if you want to do some production use right now, that'd be the one to look at. So the purpose of this particular implementation is just so the internals can be made a little more visible. But yes, A and B is the basic information needed. Anyone else?